Okay, let's dig into this one. DeepMind just dropped Dreamer 4. And if you're working on agents that need to plan long-term, this feels like a really significant step.
Yeah, absolutely. The core mission here is cracking these complex, long-horizon control tasks using basically just imagination training.
And the headline achievement, which we should probably just state up front for, the quick summary.
Right. It's the first agent ever to solve the offline diamond challenge in Minecraft, which is huge.
Define that for us. What does solving that actually mean in Minecraft?
It means starting from scratch in this, massive 3D world that's different every time. You have to gather wood, make tools, upgrade them stone pickaxe, then iron, find iron, smelt it.
All leading up to finally mining a diamond.
Exactly. And the kicker. It learned to do all of this purely from looking at an existing data set of gameplay, no interacting with the actual game during its learning phase.
Zero interaction. And that whole sequence, finding a diamond, it's something like 20,000 actions? Mouse clicks, key presses?
Yeah, easily over 20,000 low-level actions.
Yeah.
A long, long chain of dependencies.
So how did they pull this off? What's the core tech?
Two main things, really. First, a massive, very scalable world model. They built it on an efficient transformer architecture. We're talking 2 billion parameters here.
2 billion for the world model. Wow. Okay, and the second?
That's the bit that enables the speed. A new training objective they came up with called shortcut forcing.
Shortcut forcing. And that lets it run fast.
Incredibly fast. Like real-time interactive inference on just one GPU, even with that huge model.
Okay, so putting it together. Scalable world model, super fast inference. That's the recipe.
That's the recipe for this imagination training. And the results show it's way more robust and efficient. I mean, compared to something like OpenAI's VPT, which was kind of the previous benchmark.
Right, the video pre-training model.
Yeah. Dreamer 4 got better results on this diamond task using something like 100 times less data.
100 times less data. That's not just a small step. That changes the game for offline learning, doesn't it?
It really shifts the goalposts for what we thought was possible with world models trained offline.
Okay, let's zoom in a bit. Why Minecraft? Why is getting a diamond in Minecraft considered such a brutal benchmark for people maybe less familiar?
Well, it combines a lot of hard problems. You've got raw pixel inputs, high-dimensional stuff. You're controlling very low-level actions, tiny mouse movements, key presses.
Not abstract commands like go left or pick up.
Exactly. And the world is huge. It's procedurally generated, so it's never the same. And the reward, finding that diamond. It's incredibly sparse. You do thousands of things right before you get any positive signal.
So it forces the agent to actually plan long-term, not just react to immediate things.
Precisely. And the offline aspect is critical. Why focus on learning only from data you already have?
Right, because in the real world, especially with robots, letting an agent just explore randomly online can be slow, expensive.
Or dangerous. Imagine a robot arm learning assembly. Mistakes cost time, maybe break things. If you can get robust, long-horizon learning done purely in simulation, purely from data.
Before you ever deploy it. That's a massive win for safety and efficiency.
Huge, especially for physical systems.
So looking at the results table in the paper, Dreamer 4 actually gets the diamond, 0.7% of the time?
Yep, 0.7%, which might sound low, but you have to compare it to the baselines.
Which were?
VPT, even their fine-tuned version, standard behavioral cloning, other models like VLA,
yes.
They all got 0.0%. On the diamond task itself.
0. Okay, so 0.7% is infinitely better than 0. It shows imitation alone just doesn't cut it for these really long planning horizons.
Absolutely hammers that point home. And it's not just the final diamond goal. Look at the intermediate steps.
Like getting the stone pickaxe, or the iron one.
Exactly. Dreamer 4 gets the stone pickaxe, I think it was, 90% of the time. And the iron pickaxe, 29% of the time. Way faster and much higher success rates than just trying to clone behavior.
So that imagination training layer is clearly adding something beyond just mimicry. It's exploring, refining.
It's simulating possible futures and learning from them without needing the real environment. And again, that data efficiency number is key.
Remind us.
Dreamer 4 used just the 2,500-hour contractor data set from the VPT paper. VPT itself, to get its best comparable results, use that plus a fine-tuning stage on 270,000 hours of YouTube videos with synthetic labels.
Oh, okay. 2.5K versus almost 270K hours. That's the 100x difference for better performance on the hardest task.
It's dramatic.
Okay, so we see the results, we see the efficiency gain. It must come from a pretty different underlying engine. Let's talk about how this 2 billion parameter imagination engine actually works.
Right. So the basic philosophy follows the previous Dreamer models. You learn a world model, and then you train your agent using reinforcement learning inside that fast, accurate simulation.
And they break the training down into 3 distinct phases. Phase 1.
Phase 1 is world model pre-training, basically teaching the model the physics and visuals of Minecraft.
How does it learn that?
They train 2 parts: a tokenizer, which compresses the visual input, and the dynamics model, which predicts how things change. They train these on videos and actions using techniques like masked auto-encoding on those compressed representations. It builds a general understanding.
Got it. So it learns what Minecraft looks like and how it generally behaves. Then phase 2, agent fine-tuning. What happens here?
This is where they start connecting the world model to actually doing tasks. They add special agent tokens into the architecture.
Agent tokens.
Yeah, think of them as placeholders for the agent's goals and plans. They fine-tune the model now to predict not just the world, but also the agent's policy, what action to take, and the expected reward, conditioned on task information fed into these agent tokens.
So it learns to associate states and goals with actions and outcomes, kind of like behavioral cloning plus reward prediction.
Sort of, yeah, using multi-token prediction for that. And then comes phase 3, the real core, imagination training.
This is the RL part.
This is the RL part. They use an algorithm called PMPO preference optimization plus a value function to optimize the agent's policy.
But the key distinction is
the entire training, all the trial and error rollouts for the RL, happens inside the world model's predictions. No interaction with the real Minecraft environment at all during this phase.
Right.
It's all simulated.
just imagining futures and learning from them. Okay. Now, you mentioned those agent tokens. There was a really neat architectural trick they used to avoid, what was it, causal confusion?
Yeah, that's super important. Causal confusion is this risk
Yeah.
where the model might start hallucinating things happening just because the goal wants them to happen.
Like if the goal is get diamond, the model might predict a diamond appearing out of thin air because that fulfills the goal rather than simulating the actual physics.
Exactly. It confuses the agent's intention with the world's dynamics. To stop that, they design the information flow very carefully. The agent tokens, which carry the task goal, can attend to all the other information, the visual state, the past actions. But, and this is the key, none of the other parts of the model attend back to the agent tokens when predicting the world's dynamics.
So the part predicting physics only looks at past physics and actions. It doesn't get influenced by what the agent wants to happen.
Precisely. The dynamics prediction stays pure, focused only on simulating the physical consequences of actions in the current state. The goal doesn't taint the physics engine, so to speak.
That's a clever way to isolate those different reasoning processes. Okay, let's shift gears to the architecture itself. Making a 2 billion parameter model run fast enough for this imagination training, let alone real-time interaction, that requires some serious engineering.
Absolutely. Speed and scale were huge challenges. Previous world models often struggled with complex interactions or were just too slow for this kind of intensive RL training.
So that shortcut forcing objective you mentioned earlier, how does that deliver the speed?
Right. Think about standard diffusion models. They're powerful generators, but they often need like 64, maybe hundreds of sequential steps to refine a prediction or generate an image well.
Which is way too slow for interactive simulation.
Way too slow. Shortcut forcing is inspired by related ideas like diffusion forcing, but it lets Dreamer 4 generate these complex future representations in just 4 sampling steps. K equals 4.
4 steps instead of 64 plus, that's a massive speed up.
Huge. It's like taking 4 giant leaps into the future prediction instead of lots of tiny steps. And that's what gets them over 20 frames per second on a single H100 GPU. Real time is suddenly possible.
But usually there's a trade-off, right? If you take fewer steps, don't you lose quality or fidelity? How did they avoid that?
That ties into another key change they made, switching the prediction target. Instead of predicting the velocity towards the clean data, like many diffusion models do, V-prediction,
They predict.
they predict the clean representation directly. It's called X-prediction.
Why does predicting the clean state directly help?
Because V-prediction, predicting the velocity or the noise, often introduces high-frequency errors, like little bits of static or noise. When you're simulating thousands of steps, these tiny errors accumulate rapidly.
So you get visual glitches, things start looking weird over long simulations, hallucinations.
Exactly. By predicting the clean X directly, they avoid that buildup of high-frequency noise. It allows for much higher quality, temporally consistent rollouts, even very long ones.
Okay, so X prediction maintains quality, shortcut forcing gives speed. Makes sense. They also mentioned a specific loss weighting, a ramp loss weight.
Yeah, that's a neat little optimization. The weight for the loss, tau, increases linearly with the signal level, tau. It's Dirac tau plus Dorian 1L.
So losses with a stronger signal get more weight.
Right. It basically tells the model,
Yeah.
focus your learning capacity on the parts of the prediction where there's clearly something important to learn, and don't sweat the small stuff or the noisy parts quite as much. Efficient use of parameters.
Clever. And then there are the transformer architecture details themselves. Scaling up to 2 billion parameters means you have to be smart about memory and computation.
Oh yeah. They used a bunch of techniques. It's a block causal transformer, so it processes time in chunks. Crucially, they separated the attention mechanisms.
How so?
Instead of doing full attention over space and time in every layer, which is super expensive, they mostly use space-only attention layers and then only sprinkle in time-only attention layers once every 4 layers.
So it focuses on spatial details most of the time and only checks temporal connections periodically.
Exactly. Saves a ton of computation, keeps the latency down, but still captures the necessary temporal dynamics.
And they used grouped query attention, GQA.
Essential for memory.
Right.
GQA significantly reduces the size of the key value cache, the KV cache. That cache is often the biggest memory bottleneck when you have really long sequences or huge models.
So GQA is a big reason they could fit this 2B parameter monster onto one GPU and get real-time speeds.
Absolutely critical for that. They also did things like alternating short and long training sequence length to balance efficiency with the ability to generalize to longer rollouts.
Wow, okay. That level of detail really shows this is geared towards actually building and scaling these things. Now let's talk generalization. How well does this learned world understanding transfer?
This is where it gets really interesting, especially for practical applications. First, consider how much action data they needed.
Right, you mentioned the data set was 2.5K hours of video, but not all had paired action.
Correct. They found they only needed about 100 hours of video with the corresponding actions labeled. The rest was just unlabeled video.
And using only that 100 hours of paired data gave them what?
It achieved 85% of the prediction quality in PSNR and basically 100% in SSIM compared to training with all the available action data.
That's profound, actually. It means the model learns the world's rules mostly from just watching, right? It only needs a little bit of action data to connect its understanding to control.
Exactly.
Yeah.
It implies you can leverage vast amounts of unlabeled video data, which is way easier to get, and just need a small amount of labeled actions for grounding. That could massively change how we gather data for agents.
Huge implications. And then there was the out-of-distribution test.
Yeah, this was cool. They trained the agent mostly on the standard Minecraft overworld environment. Then they tested its prediction ability in totally unseen areas like the Nether or the End.
Which look completely different blocks, different physics even.
Totally different visual domains. And yet, the action prediction quality held up surprisingly well. About 76% PSNR, 80% sim fidelity compared to in distribution.
So it wasn't just memorizing overworld physics, it learned a more abstract concept of actions and consequences.
It seems so. Suggests a deeper understanding that can generalize, which is crucial if you want to use, say, diverse web videos for training foundation models.
Right. And finally, because it's so fast, humans can actually interact with it.
Yes. The real-time simulation quality is high enough, thanks to X prediction and shortcut forcing, that a human can play inside the simulated world generated by Dreamer 4.
And it handles complex interactions.
Pretty well. They tested 16 complex tasks, like building structures, using crafting tables, fighting mobs. Dreamer 4 simulations supported 14 out of 16 successfully.
Compared to other models like Lucid V1.
Which apparently failed on all 16 in their tests, likely due to simulation instability or hallucinations. Dreamer 4 runs at 21 FPS interactively.
That opens up possibilities for human-in-the-loop training or testing directly in the imagination space.
Definitely, though they are candid about the limitations still.
Which are?
The temporal consistency is good, but currently limited to about 9.6 seconds before potential drift. And predicting the inventory state precisely over long periods is still a challenge. It sometimes gets quantities wrong.
Inventory is tricky, involves tracking lots of little items accurately over time.
Exactly. So, wrapping it up, the core value here is Dreamer 4 being a major step forward in scaling world models for offline RL in really complex high-res environments.
Driven by that efficient architecture, shortcut forcing for speed, X prediction for quality.
Yeah, it's a powerful combination. They conquered the Diamond Challenge via offline imagination.
But as you said, the model's not perfect, memory limits, inventory tracking, so Thinking ahead, what's the next big challenge in Minecraft that would really push the boundaries beyond just getting the diamond? What's the litmus test for the next generation?
That's a great question. Since the current weak points are long-term memory and precise state tracking like inventory, I think the next frontier isn't just a longer action sequence, but one that demands perfect state maintenance over time.
Okay, like what specific?
Maybe something like a complex crafting and logistics task. For instance, require the agent not just to get one resource, but to manage a whole supply chain over, say, a full hour-long episode. Mine iron, smelt specific numbers of ingots, then craft a sequence of dependent items, maybe like shears, then a bucket, then use the bucket to get water for farming, then use shears for wool. Something that requires remembering exactly what you have and planning multiple steps ahead with precise resource counts.
Ah, so it forces the model to integrate that long-term memory and nail the inventory coherence, not just brute force a sequence.
Exactly. That feels like the true test of scaling beyond diamonds, mastering sustained, precise state management within that imagined world.
That makes a lot of sense. Tackling that long-term state coherence is definitely the next mountain to climb. We'll definitely be keeping an eye out for Dreamer 5 or whatever comes next building on this.
Me too. It's exciting stuff.